So what I'm going to talk about is probably very different from what you've been hearing today. I'm going to look at this from a purely computer systems perspective. So I'm going to not worry about neuroscience at all for a while. I'll mention a few connections at the end. I have actually been worked with a bunch of different people who presented here. So I do have some connections to the community, but I'm going to give you a very different perspective to get started. So there are sort of a very broad, I'm painting sort of computation in very broad brushes, right? So I'm saying that, I can think about computing as sort of discrete versus continuous time and value. And three of these quadrants are usually very well accepted by the broad, I call it the chip design community. And, we're all using components that have these properties. But this quadrant, I would argue, is relatively less explored. Where there's a small group of people that are doing very interesting work, I think, at least in this area. But it's a much smaller community, so that's what I'd like to sort of talk about today. We've already heard a little bit of this. The basic difference between the asynchronous and synchronous computing communities are the way you send information, right? So in an asynchronous computation, you've got a centralized clock or multiple clocks, and depending on how fancy you want to get. That clock is a signal that's sent to both the transmitter and receiver if I want to communicate. And the nice thing about it is it discretizes time for me. And so as a result, my signal can do whatever it wants as long as at the discrete sampling time windows, which are periodic, the signal has a well-defined value, and then I'm done. Anything else is fine as long as the signal is well-defined at those points. In the asynchronous world, we don't have this signal that tells us globally when to look at values, and as a result, you have to replace that signal with something else. And there are a number of different ways you can do this. I teach a class on asynchronous computing where I literally spend a couple of lectures talking about all the different options. But the one obvious way to do it is to use actually something from information theory, a very old idea of delay-insensitive codes, where you can encode information so that you can correctly read what value has been transmitted with arbitrary delays on wires. The other approach is to use sort of timing information, where I send the data, and then I send a signal that says you can look at the data now. So you can view this as sort of the local sampling signal, if you like. And that requires some timing assumptions, and that's fine, and you can do that as well. There are a number of different approaches to this. So the point is you have to actually do something different to transmit information. And even the simple example shows you that, I may need more wires to send the same amount of information, and as a result, that's going to maybe lead to a bigger circuit, right? So there's a trade-off here. What I get for that is the fact that not every step of my computation has to take the same amount of time, right? I get to pick what my timing budget is based on what I'm computing, and you can use this to your advantage. The other big difference typically is the way information is synchronized across the computation. So in a clock system, what happens is you've got temporal synchronization, so you have these barriers that are demarcated by the clock. So if you're used to writing parallel programs, this is global barrier synchronization. The barrier is periodic. Every computation has to be done before the barrier, and at the barrier, information is exchanged globally. In an asynchronous computation, instead, you send explicit messages, right? So I only wait for the things I depend on. I don't wait for anything else in the system, right? Because there's no global barrier. It's a local synchronization based on information and message passing. So that's another big difference. And of course, you can imagine that the fact that I have to send this message might incur some overhead. And so the name of the game is that overhead worth it, right? If it's worth it, then I can be more efficient in this way. If my computation is organized so that everything has already been perfectly matched in delay, I'm just going to see overhead, and I'm going to be slower, right? So you can see that depending on what you're computing and how your computation is structured, this may or may not be a great idea. The differences at a glance, so this is sort of a quick summary. So we've already talked about continuous time versus discrete time. The other interesting difference is that the delay you observe in an asynchronous computation is based on what you're computing, right? So it's the average over all the computation that you've done, right? So if I've done 100 steps, I sum up the time for those steps, and the average delay is what I got, right? Whereas in the synchronous case, you have to wait for the slowest step at each time because your time budget, your barrier synchronization budget has to be long enough. Another side effect is this clock is a global signal that has to be distributed across the chip, and you can do very aggressive things with clock gating, but fundamentally this is an issue. In the asynchronous case, essentially what happens is because you get switching activity in your computation when you send information, right? So there's local switching activity from basically data-driven computation. So that's actually might lead to low power computation, right? So that's another reason people look at this. The throughput's determined by sort of the speed of the devices. So if I have faster devices, my circuit's going to run faster. I don't have to figure out what that is and have an external timing signal that does that. Okay, there are asynchronous circuit families that you might have timing requirements, but you have a choice. It's not a given because like there is in the synchronous domain. And we've already talked about the encoding overhead. The one thing I wanted to tell you, and I put biased in parentheses because this is clearly not an exhaustive list, so I just picked a few things, is that asynchronous computing is really not a new idea. In fact, computers started out this way. Okay? In fact, probably the first description of this is the proceedings of the Princeton workshop, where they describe the blueprint for what's referred to as the von Neumann computer. Right? They talk about why you should be doing things asynchronously even there. There's a whole theory of switching. There's this classic book by Miller on switching theory. It's got large sections on asynchronous design. A lot of the initial machines were, I can't see the gray, like the ILIAC 2, the Atlas, and MU5 at the University of Manchester were actually asynchronous machines. Actually, there's a great quote from a report at the University of Manchester that says, of course you have to make this asynchronous. I mean, it's the natural thing to do. Putting in a clock was never an option, right? There are a number of different projects, and I've put in sort of blue what I'll call sort of a number of different neuromorphic projects that use asynchronous logic in them as well, just to make you see that, basically, starting from AER and the early work in like Carver Mead's lab, I mean, they've always had asynchronous circuits in these neuromorphic systems, and people almost don't even question why they're there, which is an interesting point in itself. So I'm going to talk about a few different properties of asynchronous logic that people have exploited to show that you could get advantages on various metrics in computing, right? So the first one, and this is a very simple, I like this example because it's really simple, and there's actually theoretical results that show you can do asymptotically better, right? So exploiting the gap between the average versus the worst case, right? So if I'm doing simple binary addition, right, this is an age-old problem. If I'm adding 1 and 1, I know what the carry out is without waiting for the carry in. So I can actually start propagating my carry outs without waiting for the carry in. The slow thing in addition is the carry chain, right? But the point is that the amount of time it takes you to propagate depends on what you're adding. These are data-dependent operations. And this is from the von Neumann report from 1946, which says that the average latency for just ripple carry addition happens to be log n, okay, if you make certain assumptions about the inputs. And that's actually in here. What's interesting is, we build logarithmic adders all the time. This is a pretty standard thing. Synchronous, asynchronous doesn't matter, okay? But it turns out you can do a sort of a hybrid topology where you use both a normal sort of logarithmic adder plus a tree. And you get something very interesting. So there's a theorem from 1965 that says that the worst case latency of a binary addition is log n. You can't do better than that. Okay? But it turns out that this topology achieves an average latency of order log n, right? And what's interesting is you can prove that that's actually optimal no matter what the input. This topology is optimal. I may not be able to tell you what the latency is, but whatever it is, this is asymptotically optimal no matter what the input distribution is. So that's an actually very pretty strong result, I think. Okay, so this is one of the reasons I think this is interesting, right? Another interesting property is data-driven power management, right? So I said, essentially you do switching, you have switching activity when data arrives, and that's when the computation is driven, right? So the computation is driven by the movement of data through your computation structure. So this is a very simple idea which was published in 1996 by a group in, Sparsa, Denmark. And what he did was a group did this really clever thing. So you have synchronous inputs and synchronous outputs. So we're talking to a synchronous world, so there's a fixed rate at which you need to get input and output. But it turns out that the arithmetic it was a FIR filter. It was for a low-power hearing aid application, I believe. And turns out that the power consumption and the delay of their circuits that they designed was very variable, and often you were done much, much sooner than you needed the result. You could run at much higher throughput. So what they did was they put asynchronous FIFOs on either end, and then they put a circuit that monitored the state of that FIFO. And based on the state of the FIFO, they had a DC-DC converter that modified the voltage of the circuit, so that you could run it dynamically at the minimum voltage dependent on the data you're computing on to meet the throughput requirements, and they use this to save energy. Okay, so that's another. So it's just a dynamically adaptive system. There's a closed loop control, and you save energy because you're running at the lowest operating voltage, and you don't know what this is up front because you don't know what your input data is. Okay, if you knew what your input data is, I don't need to compute it, right? I know the answer already. An extension of this was some work we did a long time ago, actually, 2001, where you can actually generalize this notion in a very nice way. It turns out that you can actually build arithmetic, and we designed an entire microprocessor like this, where the data path width will adapt dynamically based on the precision you need, the number of significant bits in the number you're computing on, right? And we could show, for example, and this was from like spec benchmarks and stuff like that, which was standard benchmarks used at the time for modeling energy and delay, that on average, in a 32-bit data path, on average, you used about 10 bits were only switching. And it turns out that doing this incurs overhead, so you pay about a 20% overhead, but I get a factor of 3 reduction in switching activity, so I win, basically, right, on average. Of course, I can come up with operands where this circuit would be worse than doing nothing, designing things the conventional way, but that's just not the case on average. Okay? So there's a theme in all of these things. You can see that basically the idea is you can take advantage of what you know about input statistics and input operands and the computation structure and use that to get a benefit on average, even though in the worst case you may be worse, right? This is, if you're writing algorithms, this is like your special case quick answer. If you organize your algorithm that way, you can actually get a benefit in asynchronous computation, whereas in a synchronous computation, you'll have an additional if that has to fit in your worst case delay path, and that's actually a worse thing to do. Another sort of class of projects exploits what I'll call the elasticity of asynchronous pipelines. So what does this mean? In a synchronous pipeline, when the clock strobe shows up, data moves forward one step, right? That's the whole point. It's a state machine. The clock regulates the one state transition to the next. In an asynchronous pipeline, that's not the case. So I can have sort of the same asynchronous pipeline, but I have data flowing through it, and the throughput's going to depend on the rate at which I'm shoving data through this pipeline. I put no data through the pipeline, there's no throughput. There's some limit determined by the circuits on how fast I can shove data to this pipeline, right? So the throughput's a function of the state of the pipeline in terms of the distribution of data. Okay? And I put a little asterisk here saying asynchronous computation is robust to changes in this kind of pipelining. I could add more pipeline stages, and I'm still computing the same thing. Whereas in a synchronous circuit, if you had to add a flip-flop somewhere, you've got to basically retime the entire circuit to make sure it's still computing the same thing. And I put a little star because it turns out that there are some theoretical considerations that you have to check, and you have a proof of when this is OK. So here are a couple of examples that exploit this. So this is actually made from a chip that was done at IBM in 2002. What is it? It was an error-correcting code stuff coming from a disk drive. It was processing data coming from a disk drive. It was running the error-correcting codes. And what was interesting is that the data is coming off the drive at a variable rate. It depends on where you are on the platter. Okay? But there's a fixed, if you look at the computation you have to do to decode the information, the latency is fixed. It just depends on the depth of the circuit. And so what they did was something kind of interesting. They used an asynchronous circuit to do the computation. And then you know what that depth is. You know the rate at which data is coming off the disk. That tells you exactly how many clock cycles that delay happens to be. And so they had this filter topology where the synchronous input and output took a variable number of clock cycles depending on what the rate at which data was being fed in the system. So they actually built this, and I mean, actually it shipped in production for a while. Another project that this was something my group worked on was using this in FPGAs. So if anybody has used FPGAs, you know that the interconnect delay is killing you. It's about 80 to 90% of the delay, depending on who you ask. And the reason for this is simply because you've got to map a bunch of gates to your FPGA, and you don't know where the gates are going to end up, because you know that only after you've run place and route. You don't know what the design is going to be. Okay, and the FPGA industry has done actually a remarkably good job of designing the FPGA, so it does a good job most of the time. But you can easily get to a bad signal path. And the fact that the signal path has a bunch of switches on it, which are not exactly a wonderful thing, especially if you do them with pass transistors to save on area, is that this signal path is really slow, and that's what's killing you. You can try to pipeline the signal path. That's what you would do if you were building an ASIC, a custom digital chip. You would pipeline the signal path and retime the entire system and get the throughput you want. But the problem is you don't know what pipeline you need to add because you don't have the input, you haven't placed and routed it, right? You only know how to pipeline the system after place and route. And that's too late, because if you get new inputs, then you have to add new flip-flops and retime it, then you have to replace and route, and you're not going to get the same placement. So that's the problem. In fact, actually, there was a project that was done where they tried to do that, and they basically found that the CAD tools really couldn't work. They tried to actually do it. It was actually an impressive effort. It turns out in the asynchronous case, because my data tells me when it's there, right? The computation is data-driven, the pipeline's elastic, I can put circuit-level pipelining in the interconnect. And it's transparent to the CAD tools. And as a result, if you have a computation that actually has a good data flow organization, you can get very, very high throughput on these FPGAs, right? Of course, if you have computation that's limited by long, data-dependent loops, not going to help you. In fact, it might make things worse because I put pipelining circuits on the interface, and that might be slightly slower, okay? The next category of things is, oh, by the way, if you do this for a throughput-intensive benchmarks, you get about factor of 3 improvement in throughput, okay, which is like, that's not for anybody who does digital design, a real factor of 3 is nothing to laugh at, okay? It's hard to get a real 20%. Another property people have exploited in asynchronous logic is timing robustness, right? So remember, the delay of the circuit, the computation throughput's a function of the delays of the gate. So if they happen to change, for example, if the temperature moves, circuit's still going to work. Well, it depends, okay? You can do crazy timing things and asynchronous stuff too, and those circuits will break. But you can design circuits to be very, very robust to timing. And the FPGA that I showed you was actually one of those circuits. And so we actually did a fun sweep where I got to go to a physics lab and play with liquid helium. It's not so, by the way, if you see this, that's actually the air frozen around the helium feed, right? That's what that is. The moisture from the air is frozen solid. You can play with liquid nitrogen, that's easy, but don't try it with helium. Anyway, so we have data at like 12 Kelvin running, the chip running, which is kind of amusing. It's not really a CMOS device at that point, okay? But it's running. Of course, this is well known. 77 Kelvin is like the sweet spot. It's actually nice because that's liquid nitrogen. And this is 294, the room temperature, and we heated it up as well. And these are just voltage sweeps and the throughput, right? And what's interesting is other than the 12 Kelvin for which I had to migrate everything to another lab, all of these data points were taken while the chip was running continuously. While I changed the temperature, the voltage, all of this stuff, no problem, right? We've actually done an extension of this chip which we did with BAE Systems, and this chip's actually radiation immune as well. So, if you want to put something up on a satellite, we exceed NASA's extreme environment electronics requirements of 40K to 400K, radiation immune. Actually, NASA couldn't get this test chip to fail on that tester, so we don't know what the error cross-section is. There are other things you can do to exploit timing robustness, which is to try to run as fast as you possibly can imagine, right? So this is some work from Ivan Sutherland's group. This is actually from his group when he was I think he was still at Sun Microsystems at the time. Sun was still there. They created this asynchronous logic family where basically the throughput is 6 FO4, so fan out of 4 delays. For those of you who are not familiar with this, it's really hard to reliably get a digital circuit to oscillate below that, okay? So this is you can't really go faster than this. And of course, nobody builds chips that do this normally because it's really hard to distribute a clock at that period. And you get it slightly wrong and everything breaks. Whereas here, you get it slightly wrong, that little local part of the circuit is going to run slower. And that's about it, right? So you can get timing robust. You can use the timing robustness to push your frequency as well. So by the way, what that means is, they have a chip that they fabricated recently that runs in excess of 6 gigahertz at 40 nanometer, right? And this is with it's a lab, a few grad students and a faculty member. Of course, it's Ivan, so that's a very different world. Another characteristic that people exploit in asynchronous logic is the fact that you don't have this global clock strobe signal, which if you're an analog circuit designer is called the noise source, right? And so as a result, the noise spectrum is spread out in the frequency domain. And what that means is you can actually do an integration between your analog mixed signal logic. You can do mixed signal logic with tighter integration. And this was exploited by Philips in, what was it? It was their smart card, contactless smart cards, which were used in Europe for their passports, I believe. So this is some measured data from this. This is from their paper. This is the time domain representation of current, and that's the frequency domain representation, right? So that's the asynchronous version, that's the synchronous version, and of course, since this was from a company, there's no y-axis. The last thing I want to talk about is, in terms of things people exploit, is this continuous time information processing, which is probably the thing near and dear to a lot of people in this audience. And I wanted to pick a completely different example in continuous time processing, which is actually continuous time signal processing. This is some work from Yanis Avidis' group at Columbia. And in conventional Nyquist sampling, you sample periodically in time. In this particular sampling scheme, you sample periodically in space. Okay? And you get a sample when the signal crosses this threshold. Okay? And by the way, this is used in speech. Has been used in speech for a while. So this is not new. There are papers. Actually, it's interesting. You can actually the more interesting papers in this space are from the 50s and 60s. And then people sort of abandoned this field because they were like, oh, DSP is easy. Nyquist sampling that solves all my problems. But it's kind of interesting because when you sample in time, you basically get in-band aliasing from sampling. And you basically don't with this scheme. So they actually showed you get no aliasing from the sampling process with this mechanism. And you can do. Yeah, and what's also interesting is you sort of locally get the number of cycles that essentially equal to the local Nyquist rate. Okay, but you can show that there's a theoretical bound that's is bounded by the local Nyquist rate. So that's pretty nice. And so there's work where they're trying to build a full continuous time digital signal processing chain in this framework, okay, which is actually much harder than it sounds. And of course, there's the address event representation in neuromorphic engineering, right? We're not sure where the information's encoded. There's a lot of argument over whether we should encode information one way or the other. So guess what? We're just going to copy, right? We're going to use continuous time. Hopefully, that means it captures everything that there is. We don't know where it is, but at least we don't want to give up something by picking a particular mechanism to encode information and then discovering you're wrong later, right? Why do the people use asynchronous logic there, right? So I always like this quote from various, it's attributed to various people, but it's a sort of time represents itself, right? I don't encode time explicitly, it's implicit. The spike timing in the physical circuit corresponds to the time you want to encode, right? And what's nice is that the temporal resolution of your spike timing is not coupled to your throughput in the asynchronous context. Whereas in the synchronous context, it is because that's the temporal resolution is determined by your sampling clock, right? And of course, you get automatic power management. Spike rates are very dynamic, so you don't want to waste energy capturing the finest time range resolution when you most of the time are not actually sending a spike. So that's the main reason. And pretty much, there are plenty of projects I haven't mentioned here. I mean, I could just keep typing pretty much almost lots of neuromorphic projects, if not all. I hesitate to say all because I'm sure there are projects that don't do this. Especially, I'm referring to sort of the mixed signal analog neuron digital communication projects. Almost all of them use that. So I added this slide while I was listening to the previous talk. The benefit of not having submitted an abstract is I can change what I'm saying. It's actually a well-known result in asynchronous circuit theory that most people don't seem to have seen, which is not surprising because it's been rediscovered at least 3 times. The third time was in the early 90s. There's some results from the 60s. There are 3 communities that have the same result. One of them is the community that studies concurrent systems with Petri nets. One of them is the community that designs asynchronous circuits, and the third one is actually a bunch of mathematicians that do max plus algebras. Okay? If I look at an asynchronous circuit and I look at my signal transition, so what do I mean by signal transition? I look at a wire and it goes from 0 to 1. That's a signal transition, right? I label all the signal transitions in my circuit, right? So for every wire, I'm going to look at the ith time it goes from 0 to 1, and the ith time it goes from 1 to 0. And I number them with integers, right? I can run a simulation, and I know in that simulation run, I know when the time of every event is, right? I'll call that time. So the ith occurrence of transition t happens at that time. This is my periodic approximation, okay? This is some function of the transition, which is my phase or my offset, and I times some p star. And you can actually compute p star. There's a formula for it. Okay? Then it turns out that the gap between these two is bounded. Okay? Which means on average, the signal actually is periodic. Okay, so this is a result that people have proved at least 3 times that I'm aware of. It's bounded, it's independent of I, it's independent of T. And these results have all assumed that the circuit has to be strongly connected. So essentially, there's feedback, okay, for this to be true. So for every gate output, there's feedback back to any other gate, and in particular, back to the gate's input, right? So all of these results exist. But actually, we actually showed a recent result. This is literally, we finished this in January. So we showed that actually you don't need strong connectivity. You just need connectivity from the slowest part in the circuit to everything else, which makes sense. And we can actually prove that after an initial period, it's actually not just approximately periodic, it's exactly periodic. Okay? And by the way, this also covers synchronous logic. This is a special case, right? So all the mechanisms we know how to compute end up with periodicity, even though there's no clock. Okay, so I thought that was something interesting. And it turns out that the exact result, it's not periodic in this way. It's actually periodic on a meta cycle. Okay, you don't have to unroll this. Okay, so that's the difference, and that's why none of the previous results prove that. So just to end, I just wanted to mention that talk about where we put asynchronous logic in TrueNorth and the reasons, and relate them to what I've been talking about. So, we all know that the arrival of spikes triggers activity, and so that should be asynchronous so that I can manage power automatically with spike arrival, right? And so that's what we did. The neurons, on the other hand, leak periodically. So we actually put in a period. There's a global signal, which is a 1 kilohertz clock. It's actually a pin signal. You can set it to whatever frequency you want. So that we can add a periodic event to the system to trigger that activity. So TrueNorth actually has a combination of these two things for that reason. It's just driven by the algorithm we were implementing in silicon, right? And the core algorithm looks like this, right? So this is one of the cores. At the external timing tick, which is my periodic leak, the neuron states update, all the spikes get delivered, all the local state updates done. As part of this computation, you determine if the neuron's going to spike, and if it does, it sends a spike out into the network, which is asynchronous, which just shows up, goes wherever it wants. Right? And there are axonal delays, so you can say, what time in the future you want the spike to be delivered. The receiver, when the spike arrives, the spikes travel through the network. When they arrive at the receiver, they get delivered at the appropriate time step, and that time step's triggered by the tick, the same tick that causes the neuron to leak. Right? So it's quite straightforward. And it's all implemented with digital asynchronous logic. Why digital? Well, it's purely a pragmatic decision. Okay? I don't need to get into a religious war with analog versus digital here. It just turned out on this particular technology that we had, that was just more efficient. Okay? Change the technology, you'll change the answer. Okay? It's not that complicated. And we had to make a big chip, so we had to go with mainstream CMOS because it had to work. The spike communication network. The other problem with this spike communication network is, of course, as we know, there aren't enough wires, right? So wires are time multiplexed. So the problem is if I have, say, a spike from this part of the network and that part of the network arriving here, traffic in the network might reorder the spike arrival time. And so we actually buffer the spikes at the receiver and always make sure we deliver them in the same order, no matter the order in which they arrived. And we actually have a circuit that detects if that's not possible because of timing error. Okay? And we use the spike scheduler that guarantees deterministic computation. And actually, this is a pretty powerful thing because it guarantees repeatability, right? It's not fun to say, well, I ran this morning and it works, and this afternoon it doesn't. And we might think that you're running something on your PC and it does that. Trust me, it's deterministic. You just don't know what changed, right? But in the system like this, you really have full control, and you really know what has changed because you changed it explicitly. So you wanted to always do the same thing in this case. And so that's why we did that, because at the end, we wanted repeatability. And it turned out it wasn't that expensive, and we needed that clock anyway for the periodic periodic leak. So just to summarize, I hope I've showed you a number of reasons people have looked at asynchronous circuits. There are a number of different projects. I mean, there are far too many to list here. I just picked a few samples. It's been around for a long time, and there are really interesting properties of these circuits that you can exploit for a variety of things. And I'll end here just to thank everybody. I'd like to thank the async community. I see Steve Ferber here. He's been a long-standing member. Even when I was a grad student, I knew he was doing all this amazing work with his ARM processors. You may have seen his name up a few times on my timeline. My students who did all the work, right? My collaborators whose idea I've shamelessly stolen or displayed here for you, but I put some citations to give them credit. Some folks from the neuromorphic community that I've worked with in the past, some of them I'm collaborating with now, some of them, and the too numerous to mention, and of course, everybody who pays the bills and keeps me in business. Thank you.
So we have time for a question or two as the other speakers who want to join the panel make their way up.
There are dynamical systems that are non-periodic, right? Such as Lorentz factor or...
Yeah.
And if you implement in a digital system, right? So if you implement, say, a Lorentz attractor in a digital system,
Yeah.
why would it not be periodic?
Yeah, so this whole periodicity thing, which I mentioned, there's an assumption in this model, right? The assumption in this model is that the delays of a gate are fixed, right? Now, if I allow the gate delays to have a random distribution, that this will no longer be the case. And there are circuits, and sometimes, especially when you have physical non-determinism in your system, you don't have a guarantee on the delay of the gate that can make the decision in the non-deterministic case. And as soon as you have that, the periodicity will break. So yeah, you can model it, but it won't be with a discrete set of gates which are deterministic, yeah, with deterministic delays.